Welcome to 2.3. So this is matrix computations and the specific talking about the factorization of A into a lower triangular matrix and an upper triangular matrix. Now, before I fully get into this, this video is really meant to show more examples around the factorization, as well as what he shows at the very beginning on how to determine the inverse of a matrix that's not a 2x2. And that we can't just see by inspection. And so I had alluded in the previous section, so a couple videos ago, that there is a method to find the inverse. And so I want to kind of establish that method now at the beginning, and then get into an example, another example of a matrix that we haven't seen yet. Let's factor that into L and U to see how that works, and then talk about the second proof that Dr. Strong mentions in the textbook. And I will leave the first proof as something that you can read in, because this, as far as in the textbook goes, this section is more so just around the proving behind the LU factorization and doesn't really showcase a lot of the factorizations. And I know the previous two sections we've done it a lot, but we really haven't formally put it all together except for the last video when we did it one time. So I thought it'd be helpful, at least here, almost as a recitation to work through a problem. And hopefully that will help. Now, when we're talking about inverses to begin, and I'm looking at a matrix A, we define again the inverse so that if I multiply it, we get down to I. Now, when I'm trying to figure out what this inverse is, we're essentially solving a bunch of AX is equal to B problems and augmented matrices, essentially, or augmented problems, because we're taking A and I'm trying to figure out what columns I multiply A with to get the elementary columns in the identity matrix, which we essentially call E1, E2, E3, all the way out to En. And so again, like E1 is literally the column 1, 0, 0, 0, 0, all the way N times. E2 would be 0, 1, 0, down all the way, etc. And so when you put all these things together, depending on the dimension of the matrix, this creates essentially the identity matrix. Well, this first column comes from multiplying A and X1 together. So we're essentially trying to solve this problem. And then I'm trying to solve this problem. I'm trying to solve this problem all the way down to AXN is equal to E to the N. And so if we're trying to solve a bunch of these kind of systems, we can set this up as one massive augmented matrix, because that's really what this is. It's a massive set of augmented matrices where we're just trying to figure out what is that linear combination to create it. And so again, when I generally looked at this problem here, what we would do is we would take my matrix A and I would augment it with, in this case, E1, which we use B. And I would go through the process of putting this into upper triangular form, and then we could use back substitution to solve it. Well, this one is doing the same thing, but it's placing E2 now here. This one would be placing E3 all the way down to En. And so how we can ultimately find the inverse to a matrix, if we wanted to find it, is by setting up not in augmented matrices and systems that we need to solve, but doing it all at once. So what we could end up setting up is one big matrix of AI, where I like to use kind of just dotted lines. It's not necessary, but in the notation, we're essentially creating these separate boxes within my major matrix. And by reducing this and applying those steps to this other side, what we end up uncovering and solving by turning A into the identity matrix is the other block will be the inverse. Because it's transforming A, it's the matrices that need to multiply with A to get to I. And so I wanted to showcase this using the example that he gives, and we can technically do this with the matrices from earlier, but to help kind of walk through all of these steps. What if we essentially have the matrix A, not anything too crazy, 1, 0, 0, then he has negative 1, 1, 0, just kind of reading across the rows, and then underneath I think 0, 1, 0 if I remember right. And we're going to augment, 1, I always forget this last pivot. We're going to augment this with a 3x3 identity matrix, so 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we're going to, again, assume and act like this is the only matrix I have. And so if I go through transforming this into an upper triangular matrix, and then ultimately into the identity matrix, that's going to transform the right-hand side here into the inverse. And the technical name for this is called Gauss-Jordan elimination procedures. What we've been doing by transforming a matrix into ultimately row echelon form and then reduced row echelon form is called Gaussian elimination. It's kind of the fancy term there for named after the mathematician. And so if I want to go through and eliminate, notice again the first pivot point. Here's a 1, which is fantastic for ease of showing the problem. We want to eliminate the entry here right below that. We need to zero it out by adding row 1 and row 2 together. So I'll kind of show the transformations as we go. You should still be able to see this on the camera. I tried to make it so we could see this side of the board for when we start doing the factorization. If I add these two rows together and I replace row 2, row 1 stays the same, so 1, 0, 0, 1, 0, 0. The second row becomes 0, 1, 0. Adding here, 1, 1, 0. Notice that this third entry is already 0, so we've got our pivot. So 0, or not pivot, sorry. First column is already zeroed out underneath the first pivot. The third row stays the same. So that way there's not another step that we have to do to eliminate the 3, 1 spot. We can go ahead and start working on the next pivot point, which is here, by zeroing out the entry underneath. Notice by doing row 3 minus row 2, we're multiplying this by 1 and subtracting, we'll end up zeroing out this entry and then ultimately be done. Kind of talk about what happens if we're not. So the first row will stay the same. First row stays the same. Second row stays the same, 0, 1, 1, 1, 1, 0. In the third row, we are subtracting this from this, or this row from this row, technically with the wording. So 0 minus 0, 0, 1 minus 1, which is 0, and then 1 minus 0 is 1. And that's why we want to make sure the order is so particular, so it doesn't change the sign here, leaves it as a positive 1. So now when I get over here, though, we do still need to be careful. So 0 minus 1 is minus 1. 0 minus 1 is, again, minus 1. And then 1 minus 0 is 1. And so notice that I have the identity matrix here on the left-hand side, which means what my result is here on the right-hand side is A inverse. And if I take my original matrix for A, which I found here, if I was to multiply this with this, we'll get 1, 1, 1 along the main diagonal, the 0 is everywhere else. And so this is how we walk through the process if we need to find the inverse matrix. We can set up a system like this. You can see how there's a ton of work involved. And if we think about, again, the overall idea of trying to solve this problem and how we can solve it by using A inverse, we don't normally do that because the process is so extensive. And he gets into the computation number for this when you get into computer science and programming, the numerical methods, the number of iterations, the memory that has to get taken up, the fact that we're only doing 3 by 3, but what if this was a 100 by 100, or we had non-zero numbers and probably 90% of the spots in that matrix. The amount of memory this would take up is insane in terms of running. You would need essentially a supercomputer to walk through and do all of the operations. And there was a course I took during my master's that focused on what's referred to as sparse matrices. These matrices are massive. They would destroy my MacBook when I tried to run it in Maple, just because of memory. But a sparse matrix is mostly zeros with only a few non-zero spots, but we're now focusing on matrices that are into the 100s, the thousands by thousands, and trying to look at calculations and iterations and things like that. Given that I am trying to design this course for a high school level, I'm not going to dig too much into the numerical methods that he gets into in the textbook, so I'm going to skip over the cost of the elimination and that idea. and move into doing the factorization. And even then, I'm not going to focus too much in terms of its proof. I'm going to save the second proof and identify just a couple talking points there after doing some basic factorizations, just doing it once, just to showcase kind of one example here. And that should be enough to help give an example and be able to work through the exercises after that. Because again, we've been talking about the procedure of finding this upper triangular matrix now for a couple of videos and ultimately a couple of days. So it should be doable at that point. So that is how I find the inverse matrix. Luckily, we don't have to do this process if I'm trying to find L. Recall from the previous video that L is the inverse of the elimination matrices. But what's really nice and beautiful about L is the elimination processes that we're applying are directly the entries in L. And that's something to keep in mind here, especially through the example I'm about to showcase. So I'm going to erase this work here. And I have an example of a matrix A. And our goal at this moment is not to solve a system, but to factorize it into L and U. And just kind of walk through that process. Here on the left side of the board is where I'm going to write out my E inverses. I will put my elimination matrices underneath here to kind of track what we're doing. And so you can kind of compare just like we did in the previous video. So we're going to look at the matrix A, which is 1, 1, 1 across the top, 4, 3, negative 1, 4, 3, negative 1 is my second row. And then my third row is going to be 3, 5, 3. 3, 5, 3. And what we want to do to uncover the LU factorization is using elimination, Gaussian elimination specifically. We want to put this into row echelon form, which means I want this to be upper triangular, so I want zeros here, here, and here. To get us started, again, what's really nice in this example at least, is that when I look at my first pivot point, we have a 1, so that means the multiplication is going to be pretty clean. So if I want to eliminate the 2, 1 entry here, my E21 matrix, I'm going to multiply the top row here by negative 4 and add that with row 2. So I'm going to have negative 4, 1, 0, and then 3, 5, 0, 0, 1 in terms of this goes. Now, in terms of the actual operation, the wording, if we want to be very, very particular, I am multiplying the row 1 by 4 and subtracting that from row 2. So that means if I'm doing my inverse, remember the inverse for E21 is 1, 0, 0, 4, 1, 0, 0, 0, 1. It's literally just whatever that multiplier is. And remember that the reason why this is so nice and it seems like, okay, well, duh, right, in terms of what we have, is that as we introduce more elimination methods, this entry in particular, if we just take into account these and multiply, we start to gain that extra coefficient. That number changes and is not just what we're multiplying by. And so we have to kind of keep that in mind as we're going through. Now, when I do this elimination, let's go ahead and apply E21 to my A. We would get a result of first row 1, 1, 1. My second, so 4 minus 4 is 0. 3 minus 4 is negative 1. Negative 1 minus 4 is negative 5. Third row would stay the same. Now, depending on your level, you can do this elimination steps, multiple ones at the same time, which is really nice. But to just try to keep it simple and take it one step at a time, we now want to eliminate this 3. So we're going to multiply row 1 by 3 and subtract that from row 3. So that means my elimination matrix is going to be 1, 0, 0, 0, 1, 0, but then negative 3, 0, 1. So if I multiply this matrix by E31, so that's E31 times E21 times A. Again, hopefully this is not too far over, so you'll be able to see this work. First row, second row stay the same, so 1, 1, 1. Try to not go all the way over. Second row, again, stays the same, 0, negative 1, negative 5. My third row, though, 3 minus 3, 0. 5 minus 3, so 2. 3 minus 3, 0. All right, so apologies with this. I had brain farted because I was thinking of if we swap these two rows, notice we've already got my pivot, and then we can do the elimination, but we can actually keep going. I thought this was a case where an initial elimination didn't work, so we would need a permutation matrix, which is funny to go ahead and introduce because the next lesson, the final section of Unit 2 that we're going to discuss, involves those cases where we need to do a row swap. But the fact that this entry is not 0 means we're actually okay and that we can keep walking through the procedures. So apologize, there's going to be a little jump there from when I turn the video off to when we get back to this location. But I'll try to fade into black and then fade up, do some kind of fancy transition movie magic. So we have this E31, E21A, so we're almost upper triangular. So we need to multiply by one more elimination matrix, which is E32. Now before I do that, because I froze in terms of what's going on, remember the inverse here then for E31 is going to be the matrix 1, 0, 0, 0, 1, 0, and then positive 3, 0, 1. So my E32, now we're going to multiply the second row by negative 2 and then subtract it from here. So remember, we're thinking always in terms of subtraction. Now, when I actually write out my matrix, though, the idea is that we're multiplying row 2 by 2 and adding. So I have 1, 0, 0. Second row is 0, 1, 0. But my third row here is going to be 0, 2, 1. But that means, what I'm actually multiplying by in terms of the subtraction is negative 2. So my inverse for 3, 2 is 1, 0, 0, 0, 1, 0, 0, negative 2, 1, in terms of what I'm actually multiplying by with that subtraction. So that L there is actually negative 2 there. Now, if I do this multiplication, and I'll kind of write my final answer right here. So E32, E31, E21 times A. We'll get our final upper triangular matrix. This is going to be U. Top row stays the same, 1, 1, 1. Second row stays the same, 0, negative 1, negative 5. It's my third row that's now going to get changed. 0, 2 times negative 1 plus 2 is 0. 2 times negative 5 plus 0 is negative 10. And so I have our upper triangular matrix. I've got non-zero, 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 with zeros all underneath, where because of my elimination matrix and having my inverse, we know that if I want to figure out what do I multiply with U to get back to A, we are undoing these matrices in the reverse order that we applied them. So I would essentially have E21 inverse times E31 inverse times E32 inverse times U. This ultimate matrix here is my L. And because of the order that we're multiplying in, and this is kind of the proof and the argument that he makes in the textbook for why this works, is that if I go through and do the multiplication in this order, these entries don't get compromised. So my L turns into all of these entries together. And so I'll write this here. My lower triangular matrix for my factorization would be 1, 0, 0, 4, 1, 0, 3, negative 2, 1. Here's my matrix for L. So this is what the factorization looks like for some different types of examples. Ones in particular when we don't have to do any kind of row permutations. We don't need to swap rows because I did end up with a non-zero pivot here. And again, the idea is that if this entry had gotten zeroed out, then we need to do a row swap, and we've seen that before, and that'll be what we take a look at in the next section. So this original matrix A factors into L times U here. Notice that my matrix for L has ones along the main diagonal. So just kind of an observation to make there. Versus again, my entries there, 1, negative 1, and then negative 10. And so if we were to multiply L times U, that should take us back to here. Really quick, you can see the first row times here. Each column runs out that first row there. And so we can kind of see the combinations that'll get us there. 4 times 1, 4 minus 1, etc. So you can kind of do it by inspection real fast to see that the factoration works. So hopefully this helps in terms of showing how we can take a matrix and factor it, using what we know with changing it into an upper triangular matrix, as well as long as we kind of record these inverses, we can quickly jump in to uncover what L is and the beauty of that. So the very last thing I want to show in terms of this section, it kind of involves the second proof that he gives for why this factorization works. And I really just want to dig into one of the conclusions that he's got boxed off because, again, it's this idea of rank 1 matrices and outer products that tends to pop up a couple times. And so I thought it would be helpful to just kind of discuss what he's writing there really quickly. So again, the understanding is that when I do this factorization, remember that we can think about matrix times matrix multiplication in terms of the columns of L, and I want to make sure I use lowercase. So the columns of L, so L1, L2, all the way out to Ln, times the rows of U. You kind of heard me mention this a second ago. UN, excuse me. When I was talking about going back into the matrix for A. So matrix A here is actually the equivalent of doing column by row multiplication, which remember was the outer product idea. And so if I take L1, and I'll actually write it like this, L1 as a column vector times U1 as my row, this is a rank 1 matrix. Now if I add that with L2 with U2, again, rank 1 matrix plus, and this process continues all the way out to UN. And so just kind of an important kind of observation to make in terms of the multiplication that A is the sum of n rank 1 matrices, which was a theorem that we threw out a while back. So it's just kind of showing how this pops up again with the multiplication now. He gives a further proof into this above, and he gives two proofs in particular as to why this factors out the way that it does. So this kind of gives you hopefully a little bit of a better idea as to his reasoning when he's talking about the breakdown of column times row. And we've kind of already discussed the last thing of we've been looking at elimination where we haven't had to do any row exchanges, so we haven't had to swap any rows because each time the main diagonal is containing my pivot points. So what happens when that isn't the case means we need to introduce a permutation matrix. And we've seen that it doesn't matter when we apply the permutation. We can do it all at the very beginning or we can do it all at the very end. We can essentially change our factorization so that it looks something like this. PA is equal to LU. And this is what we'll get into in the final section for this textbook. As I'm not going to dig into the derivatives and slope fields and things like that. Again, this course is designed more for a high school student after after calculus BC and sometimes multivariable.